So then, good afternoon, everybody, for another session. And that means that we're going to try to put a little bit energy in here because it has already been a long day. Today, this session is about bioconjugation and more, let's say, the chemistry part of that, but also the applicability and the manufacturability of that. So earlier today, there was already a session on conjugation, and particularly in vitro and in vivo, which was also about click chemistry, and actually that will be my contribution to the session today. Then thereafter, we will have a contribution from Iris Biotech on linkerology, so how to really conjugate all kind of cargoes to bioconjugates. And then clearly, last but not least, we will also have a contribution from Lonza, who will talk really even more generic about the bioconjugate space, including also the manufacturability thereof. So happy to first introduce you to the first part, which is about CliCr, which is a copper-free click chemistry that we developed at Cristal Therapeutics. And that's really a versatile and diverse bioconjugation approach. So you have already seen, I think, in quite some presentations, copper-free click reagents. And the most predominant ones are BCN, DBCO, structures that, and unfortunately I don't have a pointer here, but you see that in our case it's a 7-membered ring. So the 7-membered ring clearly still also contains the alkene because it should conjugate to an azide containing compound. So that's the red part, and then on the right side, the blue part, is where we have developed approaches to conjugate compounds to. And this is a unique approach because the so-called molecule TMTHI has already been discovered in the 70s, but we make it unique as a result of the sulfoxamine moiety in there that allows us actually to conjugate ligands on the right side. So, and this is kind of the pitch, namely that CliCr is way more faster, more hydrophilic, has a much higher applicability and also attractive from a commercial perspective, a good IP protection. So all in all, we think CliCr really has an opportunity to generate optimal bioconjugates against attractive cost of goods. But then clearly, I should show you some examples of this. And then I think we really are unique position as compared to other click reagents from both the hydrophilicity as the reactivity perspective. So this figure shows you on the x-axis the hydrophobicity, so the log D, and then on the y-axis the reactivity. And I think it is obviously that CliCr is really left up, meaning the most smallest, most hydrophilic, but also having still high reactivity. So that's particularly as compared to BCN, where you see much more on the right side, the DBCO showing high reactivity, but also very high hydrophobicity, which is really unattractive for the application. And particularly, I want to point your attention to small molecules, meaning if you derivatize small molecules with, for example, DBCO, the physical-chemical features are way more dominated by such a compound. So the added value of CliCr is really better. So the general concept is that you can conjugate all kinds of compounds to each other. Hence, we call it, let's say, the new superglue. Clearly, you need on the one hand, you need to have your cargo, and on the other hand, you need to have your azide-containing molecule as to literally click things together. And what we've developed, and I show a couple of examples in the next slide, this general approach where the linker could even also contain some biodegradable bonds so that on the long run, you release your native cargo again. So showing some examples, but then first defining fields, because it's chemistry, so it can be applied really in diverse areas. And I think in the, let's say, pharmaceutical space and even going into the therapeutic space, we see these potential opportunities for applications. First of all, antibody-drug conjugates, so that's where a lot of linking chemistry is used. But also going for the, let's say, the smaller ones, the small molecule conjugates, oligonucleotide conjugates. That's also actually a new field that antibodies are conjugated with oligos. But also in view of the diagnostic labeling can also even be used. We've done it ourselves with nanoparticle conjugation. And then we could even go for, let's say, ex vivo cell modification, meaning you treat CAR T cells with azide containing sugars, and then you can conjugate any type of molecule to cells. But let's show you some actual examples. So by now we have this complete range of CliCr derivatives available. And each time you start, as you see in the beginning, with, let's say, the base compound, the building block, and that can then be stepwise derivatized into a variety of linkers, allowing for conjugation with all kinds of cargo molecules. So as a first example, I mentioned ADCs. That's what we've done some very nice collaborations on. And this is just to show you that if you derivatize one antibody with either 4 DBCO molecules, that's on the right side, or with 4 CliCr molecules, and clearly this is not to scale, but then you see already in the so-called hydrophobicity interaction chromatography that you see a significant shift in the overall hydrophilicity profile of your ADC generated. So very attractive that your compound is less hydrophobically modified, and at the same time, we had much higher conversion at shorter time frame, and that particularly in this case, the collaborator indicated, well, this means either overnight reaction or reaction over the entire weekend. And from a cost price, GMP production facilities is quite expensive. So this was really attractive, quicker, having a much more beneficial end product. So then another approach, as I mentioned, cleavable CliCr compounds. Here we worked with sRNA. We developed a linker which was able to conjugate to the amine, free amine molecule. And then all in all, we generated these disulfide constructs that via a self-immolative approach could ultimately release a native sRNA again. So that's a way of really having a construct for, in this case, oligoconjugate to a peptide, have it delivered intracellularly, and then locally as a result of the increased disulfide, the increased glutathione, have the native drug being released over time. Another example is clearly that you want to introduce CliCr already early on in the molecule for later on conjugation. And what we were able to demonstrate, and that's particularly all the work done by Matt Timmers, who will defend his thesis shortly on this, is that he nicely demonstrated that CliCr is able to resist the harsh conditions of peptide resin cleavage. So that's often done with a strong acid. And what we nicely could demonstrate that you can generate amino acids by introducing all kinds of amino acids. You can do the solid phase synthesis, and then only at the last step, so after having introduced the CliCr to your peptide, after the last step, do the cleavage from the resin, and then you still have your fully functional peptide with selectively the CliCr moiety available at your amino acid of choice. And just to point out for your background, this is not feasible with DBCO or BCM because they're not as acid resistant. So this is really a unique profile. This is clearly if you are introducing CliCr in the, let's say, in the synthesis, larger molecules, even also proteins. There you want to do that potentially also at the end. And that's where Matt also has done some very nice research on, namely that we found a way to go for so-called N-terminal specific conjugation. Again, using the, let's say, the base compound, derivatize it with the compound so-called 2-PCA, which is specifically interacting with the N-terminal, and that's specifically not interacting with just random amine moieties, just as the lysines present. And this is here an example demonstrated, and there is a nice publication just recently accepted, where it was nicely demonstrated that we had really selective, only the N-terminal being derivatized with this CliCr moiety, and not the free lysine that are present in the molecule as well. And there are quite some other examples in this publication, should you be interested into this. So what we've done, I've shown you hopefully a couple of examples, but clearly as a company we also should make sure that the compound is available on larger scale. So together with another CDMO called TBD Pharmatech, so that's really their name, it's not still to be determined, but it's a very well-known, very renowned company in Estonia. They helped us with upscaling the compound to larger scale, but also with high purity, and they also have already generated these various derivatives at larger scale. We were also able to demonstrate the long-term stability of these compounds, and not unimportantly, the processes for large-scale production can be easily transferred to GMP conditions. So from a, let's say, manufacturing perspective, that's also very attractive. And then you may question yourself, how do we get access to this compound? Well, that's easy. Namely, either you come to me directly, or you can go to Iris Biotech. Namely, there it's in their catalogus, so it can be bought online. We are very fortunate to also have a collaboration with Lonza, because CliCr has been incorporated in their so-called Bioconjugate toolbox, and I'm pretty sure Nina will talk about it a little bit later on. And last but not least, also we had a collaboration with Synaffix to apply CliCr in their ADC developments, and as you may know, Lonza did acquire Synaffix, so it's now also under the big Lonza umbrella. So in case you have any interest in the technology, please reach out to either Werner or myself, and happy to take any questions since we have still 1 minute left.